In this video, we look at a few questions on vertical motion or motion under gravity. So, the first question says, a stone is fired vertically upwards from a catapult and lands 5 seconds later. What was the initial velocity of the stone? For how long was the stone at a height of 20 meters or more? So, we'll read the question again and we'll jot down the important information that we can actually obtain from the question. So the question says a stone is fired vertically upwards from a catapult and lands 5 seconds later. So we're talking about an object being projected vertically upwards, and as is the case, we usually choose our sign convention. We're going to choose the upward direction at positive. So we're going to say the upward direction is positive, and this therefore means that our acceleration A is equal to minus g. Now for simplicity and for ease of calculation, we'll use g as 10 and not the true value of 9.81 but 10. So A equals minus g is equal to minus 10 meters per second squared. Now we're told that this stone is fired vertically upwards and returns or lands 5 seconds later. Let's try to visualize the situation, right? So let's say this is the level of projection from which a stone was fired. So the stone is fired with some initial velocity which is not yet known. It reaches some maximum height from which it's going to fall and return to the initial level of projection, right? So even though it wasn't categorically stated in the question, we have to make the assumption that the stone returned to its initial level of projection, right? So the stone rose to some maximum height, it would then stop and then fall back to its initial level of projection, right? In a time of 5 seconds. So we say that when the stone returns its initial level of projection, the net vertical displacement is equal to 0. So the net vertical displacement S is equal to 0, right? And we have a time of 5 seconds. So basically what we have is the acceleration A equals minus g equals minus 10. We have the net vertical displacement S equals 0 because of course we assume that the stone returns to its initial level of projection, and it does so in a time of 5 seconds. And what do we wish to find? We want to find the initial velocity u. So therefore we must use an equation involving t, s, a and u, and that equation is s is equal to ut plus a half at squared, right? So we go ahead and we substitute and we will then solve for u. So we have 0 is equal to 5u plus a half times minus 10 times 5 squared, and so we have 0 is equal to 5u half of minus 10, that is minus 5 times 5 squared, which is 25. So this is minus 125, right? And so we have 5u is equal to 125, and therefore u is equal to 25 meters per second. So the initial velocity with which the stone was projected is equal to 25 meters per second, right? Now let's look at the next part of the question. The next part of the question says, for how long was the stone at a height of 20 meters or more, right? So what we will do is we will find the times at which the stone was at 20 meters, and the time for which it was at 20 meters or more will be the time which elapsed between those two times, or we say the difference between those two times. So let's just represent the situation on a large diagram, right? So let's say this is the initial level of projection of the stone. The stone obviously rises to some maximum height, and let's say it's going to fall, right? So it's going to fall. We know it's vertical motion, but I'm just using different diagrams or to show the different stages, right? So it's coming back down, right? And eventually it returns to its initial level of projection. Now let's say at this level it's at 20 meters, right? So the stone will be at 20 meters on its way up, and it will also be at 20 meters on its way down. So what we will do is to find these two times, at which is at 20 meters from its launch position, and then the difference between those two times will be the answer to our question, right? So from this part, the information that we still have A, acceleration A equals minus 10 meters squared. Now we have the initial velocity, u equals 25 meters per second. And we also now have the displacement, s equals 20 meters. And we want to find t. So what we will do, as I said, is to find the times at which the stone's displacement was 20 meters from its initial or starting point, and the time which elapses between those two, or the difference between those two, will be the time interval for which it was at the height of 20 meters or more. So let's find those times. So which equation we're going to use? Same equation from before, s equals ut plus a half at squared. So we have s is equal to ut plus a half at squared. So we have 20 is equal to 25t, a half of minus 10, that is minus 5. So this is minus 5t squared. Now this is looking like a quadratic, so we'll bring all the terms to one side, and so we'll have, or we can divide 2 by 5 first, whichever whichever we can do first. Let's bring all the terms to the left hand side. So these terms come over, they're going to change sign, so we get 5t squared minus 25t plus 20 is equal to 0. And because each of these coefficients are multiples of 5, we can then divide through by 5, and so we get t squared minus 5t plus 4 equals 0. And this, of course, is a nice quadratic which can be factorized, and factorizing it gives t minus 1 times t minus 4 is equal to 0. And we will then proceed to solve the equation for the times t. So solving, we get that t minus 1 is equal to 0, which means that t is equal to 1 second, or in this case, and t minus 4 equals 0, so t is equal to 4 seconds. So therefore, this stone is at the height of 20 meters above its starting point at t equals 1 second and at t equals 4 seconds. So on its way up, it takes 1 second to reach a vertical height of 20 meters. Now obviously it will rise to a maximum height and then come back down, and it is once again at 20 meters at 4 seconds, or 4 seconds after it started its motion. So therefore, the time which elapses between t equals 1 and t equals 4 would be 3 seconds. So therefore, the stone is at 20 meters or higher or above for a period of 3 seconds, right? So we look at another question. So next question says, a ball is thrown vertically upward from a point 0.5 meter above the ground level with a speed of 7 meters per second. Find the height above this point reached by the ball and the speed with which it hits the ground. So let's represent the situation on the diagram. So I'll read the question once more. A ball is thrown vertically upward from a point 0.5 meter above ground level with a speed of 7 meters per second. Find the height above this point reached by the ball and the speed with which it hits the ground. So let this, of course, be the ground, right? Now the ball is going to be thrown from a point which is 0.5 meter above ground, and it is thrown vertically upwards with a velocity of 7 meters per second, right? Naturally, the ball rises to a maximum height where it is momentarily at rest, and then it falls back to ground, right? So this is a motion of the ball going up, reaches some maximum height where the velocity is momentarily equal to 0, and from there the ball of course will fall back to ground, right? Now in this particular case, the ball does not stop at its initial level of projection, which would be 5 meters above ground, right? What it does, it passes that, and of course it lands at the ground. So therefore, because we're talking about displacement being a vector quantity, when it rises from its initial reference point and reaches, well, as it rises, the displacement is positive and increasing, right? At the maximum height, it stops and starts to fall back down, which means it's getting back to its reference point. When it has momentarily returned to its initial level of projection, the net displacement is equal to 0. Net vertical displacement is equal to 0. But it doesn't stop there. It continues to go to ground level, and since the ground is 0.5 meters below the initial level of projection, when it strikes the ground, the net vertical displacement S is equal to minus 0.5 meters, right? So because we're treating our upward direction as being positive and the ball lands below the initial level of projection, then its net vertical displacement of course is negative and is equal to minus 0.5 meters, right? So once again, we're treating the upward direction as positive, right? And of course we use that A is equal to minus G, and for simplicity it will be minus 10 meters per second squared. So we have the vertical displacement of minus 0.5 meters, that is when the ball strikes the ground, and so we have A is equal to minus 10 meters per second squared. We have the initial vertical velocity U equals 7 meters per second, right? And what do we want to find? First of all, we want to find the height above this point reached by the ball and the speed with which it hits the ground. So the first part of the question wants us to find the maximum heights, right? So as I established before, as the ball rises, its speed or its velocity will decrease, and at the maximum height it is momentarily at rest. So we can therefore say at maximum height V is equal to 0, right? So we know that V is equal to 0 at the maximum height, and so we can look at what we have and what we want to find. So because we're interested in finding the maximum height reached, we're going to use an equation which includes the acceleration, initial velocity, final velocity, and displacement. And so we'll use the equation V squared is equal to U squared plus 2AS, right? So continuing this equation, we can just make S the subject. So we have V squared minus U squared over 2A is equal to S. And S of course represents the displacement, which of course in this case is a vertical displacement and would therefore represent the vertical displacement from its initial level of projection, right? So the question basically asks for the height above this point. Good? So proceeding, we therefore get that S is equal to 0 minus 49 divided by 2 times minus 10 is minus 20, and so this becomes S is equal to minus 49 divided by minus 20, and so S is approximately 2.5. But if we want to give the exact value, 2.95, right? S is approximately, sorry, not 2.95, 2.45, right? So approximately 2.45 meters, which we can approximate to being 2.5 meters, right? So the stone, or the ball rather, will come to rest at a height of 2.5 meters or 2.45 meters above its initial level of projection, right? Good. Now the next part says, find the speed with which it hits the ground. And for this part now, we will take this into consideration, that when it hits the ground, the net vertical displacement is minus 0.5 meters. Again, remember that we're dealing with vectors. Displacement and velocity are vector quantities, and therefore direction is important. So as the object is rising, its velocity, of course, is decreasing because it is slowing down. Its displacement, however, is measured positively in that direction, right? As it falls, the displacement decreases, and whenever it returns to the initial level of projection, the net vertical displacement is equal to 0. But since the object lands below that position, its net vertical displacement is negative and is equal to minus 0.5 meters, right? So we say that when the ball lands, it is 0.5 meters below the initial level of projection, and therefore the net vertical displacement is negative. So for this part of the question, the initial velocity still applies. So u is equal to 7 meters per second, right? The acceleration a is still equal to minus 10, right? This time the other piece of information that we have is the net vertical displacement s, which is equal to minus 0.5 meters, and we want to find the final velocity v. So we want to find v, right? And so we'll use the equation v squared equals u squared plus 2as. So we'll go ahead and we'll substitute our values. So we get v squared is equal to 7 squared plus 2 times minus 10 times minus 0.5. And so we have v squared is equal to 49. 2 times minus 0.5, that is minus 1. Minus 1 times minus 10, that gives you plus 10. This is plus 10. So we get that v squared is equal to 59, and therefore v is equal to the root of 59. So v is equal to 59. Right, so it's going to be 7 point something. It's not too smaller than 64, square root of which is 8. So square root of 59, that should be about 7.8 if I have to guess. So the square root of 59, 7.7, right? So the velocity would be 7.7 meters per second, right? Now bear in mind that we're talking about vertical motion, and of course when dealing with vertical motion, we're dealing with displacement and velocity and acceleration, of course, which are vector quantities. Now if we're talking about the body's velocity, because velocity is a vector quantity, if we treat the upward direction as positive, it means that when the body is going up, its velocity will be assigned a positive value. However, when it is falling or returning in the opposite direction, its velocity will be treated as being negative. However, the question asks for the speed with which it hits the ground. So because speed is a scalar, we would not take into consideration any sign, right? However, if we had been asked to calculate the velocity with which it hit the ground, this would have been a minus 7.7 because of the direction, right? However, because we're asked to calculate its speed, in any case, speed is just the magnitude of the velocity, and so it is simply equal to 7.7 meters per second. We look at another question. Now this question says, a stone is thrown vertically upwards with a speed of 10 meters per second from the top of a cliff which is 70 meters above sea level. Find the time at which a stone hits the sea. So I'll repeat. A stone is thrown vertically upwards with a speed of 10 meters per second from the top of a cliff which is 70 meters above sea level. Find the time at which a stone hits the sea. So again, we'll represent the situation using a simple diagram, right? So let this be sea, and let this be our cliff, right? Right? So the stone is going to be thrown vertically upwards from the cliff with a velocity of 10 meters per second. Right? We know the stone will reach maximum height and eventually it will fall. right? So the stone is going to fall and it's going to hit the sea. So as the stone rises, its displacement is increasing because it's treating the upward direction as positive, right? At the maximum height, it will be at its maximum displacement from the reference point. However, it does not stay there, it's going to fall and it's going to come back towards, come down. However, when the stone is falling, when it reaches this level from which it was initially projected, the net vertical displacement is equal to 0, right? So the stone rises to a maximum height and then comes back down and then reaches the initial level of projection, and therefore when it does so, the net vertical displacement is equal to 0. But however, according to the question, the stone does not stop there. It continues further and then strikes the sea, which of course is 70 meters below the level of the cliff, right? So the sea is at 70 meters below the level of the cliff, and therefore when the stone hits the sea, its net vertical displacement S is equal to minus 70 meters, right? So once again, the stone is projected vertically upwards with a velocity of 10 meters per second. It rises and eventually reaches a maximum height where its velocity is momentarily 0. It then falls back down. When it reaches back the initial level of projection, is net vertical displacement equals 0. But it doesn't stop there. It lands in the sea, which is 70 meters below the top of the cliff. And so therefore when it lands at the sea, its net vertical displacement is minus 70 meters. So in addition to that, what we have is this. We have u equals 10 meters per second. We have the acceleration a equals minus 10 meters per second squared. And of course, when it lands in the sea, the net vertical displacement equals to minus 70. And so we have S is equal to minus 70 meters. And what do we want to find? We want to find the time, t. So we have u, we have a, and we have s, and we wish to find the time t. Which equation do we use? We use equation s is equal to ut plus a half at squared. And we will proceed by substituting our values. So we have minus 70 is equal to 10t, half of minus 10, that is equal to minus 5t squared. We bring all the terms to one side, and so we have 5t squared minus 10t minus 70 equals 0. We can simplify this equation by dividing through by 5, and so when we do that, what we get is t squared minus 2t minus 14 equals 0, right? So t squared minus 2t minus 14 is equal to 0. And so we'll then solve this quadratic to find the time t. So it is a quadratic which doesn't look like it could be factorized, so we'll have to resort to using the quadratic formula, right? So according to the quadratic formula, in this case we have t is equal to minus b plus or minus root b squared minus 4ac all over 2a. So in this particular case, a is a coefficient of t squared, b is a coefficient of t, and c is the constant term. So we have a equals 1, b equals minus 2, and c is equal to minus 14. And so t equals 2 plus or minus root. So minus 2 squared, that is gives us 4. Then you have minus 4 times 1 times minus 14. That is all over 2a, which is 2. So we have t equals 2 plus or minus square root of. Now minus 4 times 1 is minus 4. Minus 4 times minus 14 is plus 56. And 56 plus 4, that gives us 60. So this is plus or minus root 60 all over 2. Now we're calculating time, and the time could never be negative. So from here on, we'll just ignore this negative sign. So it's going to be equal to 2 plus root 60 divided by 2. And from the previous question, I remember that root of 60, was it 60 or 59? Was about 7.7. So root of 60 or 7.8. So root of 60, right, 7.7 or 7.74. So t is equal to 2 plus 7.74 all over 2, which gives us 9.74 divided by 2. So t is equal to 4.87 seconds. So therefore, the stone takes a time of 4.87 seconds to strike the sea. All right, we'll look at a few more questions. Now, this one says, a stone is dropped from the top of a building, and at the same time, a second stone is thrown vertically upward from the bottom of the building with a speed of 20 meters per second. They pass each other 3 seconds later. Find the height of the building. So, this situation involves a stone being dropped from the top of a building, and simultaneously another stone is projected from the foot of the building with a certain velocity, right? And they meet or they pass each other 3 seconds later, and we want to find, or we're asked to find, the height of the building. So again, let's try to represent the situation on a simple diagram. So let this be the building, right? So that's our building, and of course this is the ground, right? So one stone will be dropped from the top of the building, right? And we'll talk about the significance of it being dropped later on. Whereas the other stone is going to be projected vertically upwards with a velocity of where is it? Right, so a stone is dropped from the top of a building. At the same time, a second stone is thrown vertically upward from the bottom of the building, the speed of 20 meters per second. Right? So the second stone is thrown vertically upwards with a speed of 20 meters per second. Right? Now, the first one is dropped. Now, when you drop something, that means the initial velocity is 0. So the first stone will have an initial velocity of 0. So what will happen is that the two stones will travel most likely different distances. So if this stone travels a distance, let's call it say x in 3 seconds, and this stone travels a distance y in 3 seconds, then it means that the height of the building h is equal to x plus y. Right? So what we will do is we will calculate the distance traveled by each stone in the given time, and then we will add that to give the height of the building. So for the, let's call this stone 1, and let's call this stone 2. So for stone 1, of course it is being dropped, so usually we treat the downward direction as positive, and the initial velocity of course is equal to 0. So u is equal to 0, the stone is dropped. We have A is equal to G, which is equal to 10 meters per second squared, and we are given a time of 3 seconds. So T equals 3 seconds, and we therefore want to find its net displacement, or its vertical displacement, S. Now to find S, we need an equation involving U, A, and T, and that equation, no surprises, is S equals UT plus a half AT squared, right? So this stone will travel a distance given by U is equal to 0, so therefore this part is 0. So S is equal to 0 plus a half times 10 times 3 squared. So this gives us 3 squared as 9, 9 times 10 is 90. Half of 90, that gives us 45 meters. So in the 3 seconds, stone 1 falls a distance of 45 meters, right? Let's look at stone 2. Now stone 2 is projected vertically upwards, and usually, of course, when that is the case, we treat the upward direction as positive, and A would be equal to minus 10. Its initial velocity is 20. So U equals 20 meters per second. A is equal to minus 10 meter per second squared, and at the same time 3 seconds. And same equation applies. S equals ut plus a half at squared. So S is equal to ut plus a half at squared. And so this gives us S is equal to 20 times 3 plus a half of minus 10 times 3 squared. So 20 times 3, that gives us 60. Half of minus 10, that is minus 5. Minus 5 times 9, that's 45. So this is 60 minus 45. And this gives us 15 meters, right? So therefore, stone 1 travels a distance of 45 meters, and stone 2 travels a distance of 15 meters before they meet, and therefore the height of the building is 45 meters plus 15 meters, and therefore H is equal to 60 meters. So the stone is 60 meters high. Sorry, the building is 60 meters tall. That would be a huge stone. All right, let's do one more question. So this one says, a stone is projected vertically upward with a speed of 7 meters per second. And 1 second later, a second stone is thrown vertically upward from the same point with the same speed. Find where the two stones meet. So one stone is projected vertically upwards with a speed of 7 meters per second. Excuse me. And then 1 second later, a second stone is thrown vertically upwards from the same point with the same speed. Find where the two stones meet. So basically, let me try to represent the situation on a little diagram. The key word there is try. So we have stone 1 being thrown vertically upwards with a velocity of 7 meters per second, right? So it will have been moving for 1 second when we have a second stone thrown or projected with the same velocity, u equals 7 meters per second, right? So by the time that this stone is projected, this one would have already been at some height, we don't know, moving upwards, right? However, the two stones meet. Now, chances are they will meet, well, not chances are, but it is highly likely that they will meet after the first stone has reached its maximum height and is now on its way down. Because obviously, the two stones are projected with the same velocity. So, I mean, with everything else being equal, they will never catch each other until this first stone starts to come back down. So when the two stones meet, the first stone will be on its way back down. However, the net vertical displacement from the launch position will be the same. So basically, what this means is that when they do meet, the net vertical displacement from the reference level will be the same. And this stone will have traveled the same distance, basically, or attain the same displacement, but in 1 second less, right? So we say that when the two stones meet, so their displacement from the launch position which of course is the ground. All right, just upward from the launch position will be equal, right? So because the second stone is projected 1 second after, if the first stone would have been traveled for a time, say t, and the second stone would have been traveling for a time t minus 1, right? So stone 1 would have traveled for a time of t seconds, and stone 2 would have traveled for a time of t minus 1 seconds, right? So this is achieved in a time of t seconds for stone 1 and t minus 1 seconds for stone 2. So basically both stones will have the same displacement, but this is acquired, or this is achieved in t seconds for stone 1, but t minus 1, right? I would say this achieves that in 1 second less. So we have initial velocity, and of course because we're talking about projected upwards, or acceleration A will be equal to minus 10 meters per second squared, right? So for stone 1, its net displacement will be given by S is equal to ut plus a half at squared. Now bear in mind, we don't know the times at which they meet. So we'll let the time for stone 1 be t. And this substituting the values that we have, then this gives us S is equal to 7t minus 5t squared, right? So this is the equation for the displacement of stone 1 in a time t. Now for stone 2, it would have traveled the same displacement, so we have S equals u. However, in this time, or in this case, the time is t minus 1 seconds. So this is S equals u times t minus 1 plus a half a t minus 1 squared. And we'll then substitute, and so we have S is equal to 7 times t minus 1 minus 5 times t minus 1 squared. We expand the brackets and simplify, so we get S is equal to 7t minus 7. Expanding the brackets here, this will be minus 5, open bracket, t squared minus 2t plus 1. And so this gives us 7t minus 7 minus 5t squared plus 10t minus 5, right? So we could simplify that a little bit. So the t's, right? So anyways, all right, so yeah, all right, let's leave it, because what we're basically going to do is just to equate the two of them. So remember that they would have had the same displacement, so these two s's will be equal. So we'll simply equate these two, and some of the t terms of course will cancel, right? So the distances are the same, and so what we have is this. We have 7t minus 5t squared, that's for stone 1, would be equal to 7t minus 7 minus 5t squared plus 10t minus 5. So this will cancel that will cancel that. And so we have 0 on the left hand side equals minus 7 minus 5, which is minus 12, is equal to 10t minus 12. So we have 10t equals 12, and so t equals 1.2 seconds, right? So it will take a time of 1.2 seconds. Now bear in mind that this t represents the time for stone 1. So we have to be careful now about which equation we will substitute this value into, right? So because t was used to represent the time taken for stone 1, we will then substitute that value into this version of the equation, s equals 7t minus 5t squared, right? As a matter of fact, anyways, because we equated them, then it could actually go into either, right? It should go into either, and we should get the same result. But this one obviously is much simpler, more straightforward, so we'll use this one, right? So we have s is equal to 7t minus 5t squared, And so S is equal to 7 times 1.2 minus 5 times 1.2 squared. Now 1.2 squared, 7 times 1.2, that's 7 plus 1.4, 8.4. So S is equal to 8.4. Then this is minus 5. 1.2 squared, that should give 1.44. Then when you multiply that, we get S is equal to 8.4. 5 times 1.4, that is 7.2. That is minus 7.2. And so S is equal to 1.2 meters. Right? So they would meet at 1.2 meters above their initial level of projection. All right, we'll do one last question. Now this question says, an arrow is fired vertically upwards, reaches a height of 100 meters, then falls back to earth. Sketch a velocity time graph of this motion and calculate. So, the arrow is fired vertically upwards and it reaches a maximum height of 100 meters. And we're asked to sketch a velocity time graph, right? So let's look at the information that we have. So we're talking about an arrow being fired vertically upwards. So we're going to be treating the upward direction as positive. So we say up is positive, right? So what this means now is that A is equal to minus 10. And we're told that the maximum height, so the maximum height or the vertical displacement S is equal to 100 meters. And of course we know that at that height, then V is equal to 0 at maximum height. Right, so this S of course is the maximum height. Height GHT, right. So what we're told to do first is to actually sketch a velocity time graph and calculate the initial velocity of the arrow. Now, we're talking about motion under gravity. We're taking the upward direction as being positive. So because the body is projected upwards, while it is moving upward, its velocity will be positive. So this is velocity in meters per second on the y-axis and time in seconds on the x-axis, right? So the arrow is fired. And because the arrow is fired, it will have some initial vertical velocity, right? So the initial vertical velocity will of course be positive because it's treating the upward direction as positive. As the arrow rises, its velocity decreases, and eventually, at the maximum height, it momentarily comes to rest. The acceleration, of course, is uniform because, of course, ignoring the effects of wind resistance. So this portion of the graph, from firing to maximum height, is a straight sloping line. So at this point, it's momentarily at rest. So therefore, the arrow would be at its maximum height. Now, because we're talking about vertical motion, then the acceleration will be uniform, right? Now, you might be tempted to ask, how can the acceleration be uniform when it is initially going up and it is slowing down? So the acceleration should be negative, and then now when it is coming down, it is speeding up, and so the acceleration should be positive. Now, the situation is this. We're treating the upward direction as positive. So therefore, when the upward direction is positive, while it is moving upward, its velocity is decreasing in a positive direction. So a decreasing velocity in a positive direction is actually a negative acceleration, right? Remember that acceleration is a vector quantity. So acceleration is not just a function of speed, but a function of direction as well. So we have different combinations or different permutations for a body's acceleration, right? So we have our different combinations of speed and direction. So a body whose speed is increasing in a positive direction will have a positive acceleration. If the body's speed is decreasing in a positive direction, as in this case with the arrow going upward, then that will be a negative acceleration. Good? If the body's speed is increasing but in a negative direction, that also is a negative acceleration, and this is what is happening when the arrow is on its way down. So because you take the upward direction as positive, when it is coming back down, that direction will be negative. Its velocity is actually increasing in a negative direction, and therefore the acceleration is negative and has the same value as what was going up. So therefore the graph just continues to be a straight line. Right? So that is basically what this graph looks like, and this of course is a single straight line segment, right? I know my lines are not perfect, but it is supposed to be a straight line. So this represents the velocity time graph of the arrow. And of course, as I said, ignoring the effects of wind resistance, the arrow should actually reach back its initial velocity with which it was projected. So what does that mean? If this velocity was, say, 50 meters per second, this of course down here would be minus 50, right? And so on. So equal speed, or equal magnitude, but in an opposite direction. So that basically would be the graph of the arrow's motion. Alright, so we have some calculations to do. So what do we want to find? We want to find the initial velocity of the arrow. So what information do we have to find that? We have A equals minus 10, S is equal to 100 meter at maximum height, and of course at the maximum height you know V is equal to 0, and we want to find U. So we're going to use the equation V squared is equal to U squared plus 2AS. So we have 0 is equal to U squared plus 2 times minus 10 times 100. So we get 0 is equal to U squared minus 2000. U squared is equal to 2000, which means that U is equal to square root of 2000. And so U is equal to square root of 2000. That gives us 44.7 meters per second. Right? So the initial velocity is 44.7 meters per second. Now the next part of the question wants us to calculate now the time taken to reach maximum height. So as from before, we have A, we had S, we had V, we now have U, and now we want to find T. So this was part A of the question, the initial velocity. Part B wants to find the time taken to reach maximum height. Now as of course we know that at the maximum height, V equals 0, we have A, we have U, so the most logical equation to use is V equals U plus AT, and so therefore V minus U over A is equal to T. And so T is equal to 0 minus 44.7 divided by minus 10, and that gives us 4.47 seconds, right? So the arrow would take a time of 4.47 seconds to reach its maximum height. Now, looking at our graph now, we can actually put that information on our graph. So the time value right here would be 4.47 seconds, or we could say 4.5 seconds to one decimal place, right? So the value here would be 4.5. Part C, the velocity of the arrow when it is 55 meters above the ground moving upward. So part C, they want us to find the velocity of the arrow 55 meters above the ground moving upward. Now, why is the direction important? Anyways, the displacement is 55. So in addition to what we have from before, I will see what we have which is relevant. We have the initial velocity U, which is equal to 0.7 meters per second. We have A is equal to minus 10, and we have S is equal to plus 55 meters. And we want to find V. Right? Now we're told it is moving upward, and so we can actually, when we calculate the velocity, then we can actually assign a sign to it, right? So because we're talking about the upward direction being positive, when we calculate the velocity, then it should be a positive value, right? So use the equation V squared is equal to U squared plus 2AS. So U is equal to 44.7. But of course, we square rooted for 2000 to get that. So therefore, that is just going to be 2000. So V squared is equal to 2000 plus 2 times minus 10 times 55. So V squared is equal to 2000. That's 110 times 10, 1100. This is minus 1100. So V squared is equal to 900. And therefore, V is equal to 30 meters per second. And in this case, of course, it's positive because of the direction moving upward. Now, if the question had said 55 meters moving downward, because of the direction, we would have had to put the minus sign. Because remember, velocity is a vector quantity. And if while moving up, its velocity is treated as being positive, while it is moving down, its velocity must be treated as being negative. There's one last part of the question. We're asked to find the height of the arrow 6 seconds after firing. So we have our information from before that in, right? So A is still equal to minus 10. This no longer applies. So A equals minus 10. U is equal to 44.7. And now we have T equals 6 seconds. And I want to find its height 6 seconds after firing, right? So S is equal to UT plus a half AT squared. And so we have S is equal to 44.7 times 6 plus a half times minus 10 times 6 squared. For ease of calculation, I'll just round this to 45. Makes it easier to work with. So this gives me 6 times 45, that is 270, minus 5 times 36. So this gives me 270 minus 180, which of course is equal to 90 meters, right? So approximately 90 meters.